Okay, well, thanks for having me. And today I want to talk about topology. So, but it surprises me quite that there's not been much attention so far to the topological character of the band structure of twisted bilayer graphene. So I'm going to give you a bit of an overview of what I think is the most important way to look at it. Now, traditionally, topological band structure means that a band carries a non-zero Chern number. But a more recent view is that a topology means that you cannot one-urize the band. You cannot make, like you have here, a local orbital with short-range, tight-binding hopping parameters. So you don't have that. So let's think about how that works in graphene. Now, in a single graphene layer, you have two direct cones, which we usually call valleys, and each direct cone has a certain chirality in sublattice space. And we, of course, know graphene has a tight-binding description, so there's no topology in these bands. But one way to understand that is that because the two cones have opposite chirality. In twisted bilayer graphene, however, the two cones of the two layers close to each other, they hybridize. So within one valley, there's actually two cones with the same chirality. And that means if you look at the flat bands in one valley, you cannot one-urize that. You cannot make a hopping model with localized orbitals and short-range couplings just for one valley. So these flat bands are topological. Not that they carry a Chern number, but this is a new phenomenon which is dubbed fragile topology. Now, there's two ways that you can make this topology explicit. That is, making sure that these bands actually carry a non-zero Chern number. And these two ways are either by sublattice symmetry breaking or by large magnetic field. And I will talk about both of them in my talk. Let me start with the sublattice symmetry cone. And you break sublattice symmetry, you open up a gap, and integrating that around the cone gives you a Chern number of plus or minus a half. And again, because in monolayer graphene, you have two opposite chiralities of the two cones, it does not give you a net Chern number, but you can already see what happens in twisted bilayer graphene. Each valley has two cones with the same chirality, so the moment you open up a gap through sublattice symmetry breaking, the flat bands gains either a +1 or -1 total Chern number per valley. So in the opposite valley, you have the opposite Chern number. This is a state of a quantum valley Hall effect. This was also mentioned by Ji Shan in the context of TMDs. The question is, how can you break sublattice symmetry in TBG? An easy way to do so is by adding a third untwisted layer, and this is known as twisted monolayer bilayer graphene. The idea is to start with regular twisted bilayer graphene, and then we add a third layer in such a way that it's aligned to the middle layer. So in the middle layer, the sublattice symmetry is broken. If you then calculate the band structure, you indeed find you will get flat bands separated from the rest that carry non-zero Chern number. And of course, this is in one valley. In the other valley, they have the opposite Chern number. And by tuning the perpendicular electric field here from -50 to 0 to +50 MeV, you can induce a series of topological transitions that change the Chern numbers of these flat bands. And I want to give you attention to here because for positive electric field, we found the flattest bands. So there, I'm going to look at interaction effects. And again, I want to give you an overview, an intuition. And there's an elegant way of understanding what interactions do when you have a Chern number. Because the topology, like I said, means no one-urization, means no localized orbitals, which means there's no sense of thinking of local repulsion like in the Hubbard model. Instead, because if you try to make a tight binding description, you'll get non-local orbitals that have a lot of overlap with each other. Overlapping orbitals tend to have ferromagnetic coupling with each other. This is much like you have the Hund's rule in multi-orbital systems. And it's indeed shown that in TBG, the dominant coupling between these non-local orbitals is ferromagnetic. So indeed, if you then take TBG that you induced with a Chern number by breaking sublattice symmetry, you get a system that favors spontaneous spin-valley polarization. This was shown for TBG aligned with an HBN substrate to break sublattice symmetry. And there at filling 3, they propose you have this state where one valley is completely occupied, the other valley has one spin species not occupied, which means that the net Chern number of the occupied bands is +1. So this system is now a ferromagnetic insulator with a quantized edge current given by this Chern number of +1, which is known as a Chern insulator, or alternatively, the quantum anomalous Hall effect. Now, me and my collaborators, we predicted also a quantum anomalous Hall effect in twisted monolayer bilayer graphene. So again, we start with this relatively flat band which carried, as we showed, a TC equals 2 Chern number. And because the only thing we expect is spin-valley polarization, we can just use very simple Hartree-Fock-Mean field theory, because that includes polarization, just by projecting the Coulomb interaction onto the flat bands. We showed that indeed, if you go to 3 filling of this green flat band, you again have one valley completely occupied, the other valley only one spin species occupied, and the other not, which gives you a net C equals 2 Chern insulator, or C equals 2 quantum anomalous Hall effect. And this was indeed seen in the experiments with even the right quantization here of the transverse resistance of a half, which is just 1 divided by the Chern number. Now, for the second part of the talk, I want to talk about the other way to create bands with a Chern number. This is by applying a large magnetic field. So my apologies if this is all known to you, but I want to start again with the Dirac cone. Standard Pyle substitution gives you a spectrum with Dirac Landau levels where the energy is proportional to the square root of the magnetic field, and the Landau level index n, which can be number 1, 2, 3, also negative numbers, and this is a special thing about a Dirac cone, you also have a 0th Landau level. Now, each Landau level is actually a perfectly flat band with a Chern number. In a monolayer graphene, the total Chern number for such a level is 2 times 2. The 2 comes from spin species and the fact that you have 2 Dirac cones. But if you include the lattice, you'll get a much more beautiful fractal energy spectrum known as the Hofstadter butterfly. And this small region here down in the middle, that's determined by these Dirac cones, but outside it becomes much more complicated and depends on the specific band structure. So the question is, what do you expect for the flat bands of TBG? To compute those, we use the continuum model approach. And the idea is we start with the Landau levels of the Dirac cones that you got from each layer. It gives us a basis state of orbitals with index, the Landau level index, the momentum in one direction, and of course the layer spin and valley index, which I didn't write here. Now the Moiré interlayer coupling, what it does, it is proportional to a plane wave, so it allows for transitions between different Landau levels with a different Landau level index, and also it changes the momentum of this Landau level state. So if this is just an exact diagonalization problem with a suitably high Landau level cutoff, you can solve this and you get this beautiful Hofstadter butterfly. And I just want to point to you that, again, you would have here this square root of B Landau levels, which comes from now the renormalized Dirac cones. And it actually looks a lot like what you expect for a regular honeycomb lattice like graphene. Note, however, that you would not get such a nice result if you would try to compute the butterfly using one of the tight binding models of TBG. You get a completely different result. But since the experiments that I'm going to show you now seem more consistent with this butterfly that we used with the continuum model, I'll stick to that for the moment. The main structure of this butterfly can be summarized as follows: that in the middle of the spectrum, there is the 0th Landau level, which carries a Chern number of +2 per spin and valley. And because the total bands should carry 0 Chern number, that means that the 2 parts on the left and right should each carry C equals -1 Chern number per spin and valley. Now, the black lines that you see here, that constitutes this fractal exact Hofstadter spectrum, but due to disorder and finite temperature, these bands are broadened. So instead of a density of states that looks like this with many peaks here, example at 1/7 flux, you get something which is broadened by disorder. And indeed, the main thing we find is that this gap between the blue and yellow and blue bands, that's the thing that's the most prominent feature. So the summary is, from all this theory, the butterfly, the spectrum at a magnetic field gives you 3 bands with a Chern number -1, +2, and -1. Now, as I argued before, when you have these bands, the interactions prefer spin valley polarization. And this can be easily described with the Stoner mechanism, which is even a simpler version of standard mean field theory. Polarization just happens when the effective interaction times the density of states equals 1. So you take this density of states I just calculated, you find what the interaction strength is, and if it's strong enough, every time your density of states comes above it, the system will polarize. And that's what we expect then when you start to fill, starting from a completely empty flat bands. You start to fill all the 4 spin and valleys. At some point, you hit this point where the interaction is stronger than the density of states. And then you fully occupy with 1 spin or valley flavor this C equal -1 band, and the rest is reset, which gives you a C equals -1 Chern insulator. This is repeated. Like you do the same thing with the remaining 3 flavors. You get a C equals -2 Chern insulator, and then a C equals -3 Chern insulator. So this is what we theoretically predicted, and this is actually inspired also by similar experiments in zero magnetic field, where you get this all filling and then a reset. It was done, I think the first people who suggested that sequence of spin valley polarization was the Zondiner paper beginning of last year. Which brings me to our own experimental results, which were done by Yu Saito and Andrea Young in Santa Barbara. This is, I think, the main result. It's magnetotransport of magic angle TBG in a magnetic field up to 12 Tesla at a temperature of 4 Kelvin. So what the colors here are just longitudinal resistance. And every time you see this dark diagonal lines, that corresponds to an insulating state. In particular, it corresponds to a Chern insulating state. And rather than like staring at this picture, we can extract like the relevant states out of it. Each of these lines correspond to a Chern insulator state. Here with this cartoon picture, you see it's indeed this sequence of -1, -2, -3, -4 Chern insulator states. I can even drive that home a bit more by looking at explicitly how this data looks at, for example, 10 Tesla, which is about 2/5 flux, where we see that you get a -1 state where we just expect that this blue band of the Hofstadter is only occupied with 1 flavor. And then you get a -2 state where it's occupied by 2 flavors. And there's the -3 state where it's occupied by 3 flavors, and so forth. After the -4, it goes back to 0 because you start to occupy this +2 Chern band, the 0th Landau level, and that compensates and brings the state back to a 0 Chern number insulating state. Now, when you go down in temperature, you will resolve more of the features of this Hofstadter spectrum than just these 3 bands that I showed. That was more of a, what are the most robust features. So this is the same measurement as before, but now at 10 millikelvin. The -1, -2, -3, -4 Chern insulator states are still there, but there's a lot of new features. And in particular, if you zoom in here, you have some new insulating states with Chern numbers that indicate in this red line here, this is the measurement, this is the cartoon, this red line indicates that in the Hofstadter spectrum, C equals +2 subband is actually split into 2. This is a next order effect. You cannot describe this with regular spin valley polarization, so you need some spontaneous symmetry breaking within one spin valley species. And there's various candidates like nematicity or a charge density wave, but we still don't know the exact nature of these, what we call symmetry broken Chern insulating states. But these main states, these -1, -2, -3 sequence are, I think, well established because there's also several other groups by various experimental techniques who have seen the same sequence of state. And I think this kind of establishes spin valley polarization as something that's reliably reproducible phenomena in TBG. So before I end, I just want to thank my collaborators, of course, the experimental collaborators, Yu Saito and Andrea Young and Jingwan Jie, and of course, everyone has Kenji Watanabe and Taniguchi. The theory was done in Geneva with Ivan and Dima and Paula also in Chile, which brings me to my conclusion slide. I showed that the fragile topology can be made robust in either twisted monolayer bilayer graphene or by applying a large magnetic field. And in both cases, spin valley polarization creates correlated Chern insulators, and you can, on a theory level, just describe that by simple Hartree-Fock theory. And I just want to end with, if I may, with maybe a controversial thought, because this mechanism of spin valley polarization is so robust, we've seen it in so many experiments, it suggests that maybe TBG is not at all like cuprates or heavy fermions, because the spin valley polarization is not a mod insulator, it's just a simple Stoner ferromagnet. And if this is really true, it's unlikely that we will learn anything about cuprates and high TC superconductors from studying graphene Moiré structures. So with this final thought, thank you for your attention, and I'll be in a gather town after Jose's talk.